Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is chapter 2, which is limits and their properties. All right. 2.1. 2.1 is called a preview of calculus. I will actually not be covering this section. Um, Essentially, what it talks about overall is why we need calculus. And the short answer to that is calculus is the study of change. And in general, we analyze how things change using calculus. But again, I'm not going to be covering too much of this. In fact, I am done covering 2.1. 2.2. So I'm done covering 2.1 because you'll see throughout the course what we mean by this statement of calculus is a study of change. So let's go ahead and begin with 2.2. 2.2 is find the limits graphically and numerically. So finding limits graphically and numerically. So here we go. Consider the following function. Consider that you have f of x being x cubed, x squared minus 3x plus 2 over x minus 2. All right, now this function can be rewritten. All right, it can be rewritten. If I factor the numerator, it will be factored into x minus 2 times x minus 1, all of this over x minus 2, right? So in here, that is what the actual function factors to, right? That is as long as, well, what we see now there is that the x minus 2's cancel each other out, right? And that gives us the statement of x minus 1. Now, this is only true as long as x does not equal 2, right? Because from the beginning, from over here, we can say that the domain is x is not equal to 2. So this function just simplifies to be x minus 1 for all the values where x is not equal to 2. So what we can say now is, well, let's look at the graph of this, all right? So it's going to look like x minus 1. Now, x minus 1 is a linear function, right, that has a slope of positive 1 and a y-intercept of negative 1. So it looks like this, all right? For the most part, that's what x minus 1 looks like. But we have here that x cannot be equal to 2. So what that tells us is that when we go to 2, we have a hole here, all right? There's going to be a hole there. So there's nothing inside of that hole. And well, what we really want to figure out here is, well, what happens near 2, right? Now, this height here is at the height of 1, right? So that value there, if I were able to plug into the function, well, 2 minus 1 is 1. That's why it would be at the height of 1. That's where the height of that hole would be. But the idea here is that, well, even though we don't know what happens exactly at 2 in the sense of it's undefined, all right? So we can say here overall what's really happening with the function. I can rewrite the piecewise function, excuse me, I can rewrite this function as a piecewise function as x minus 1 wherever x is not equal to 2 and undefined wherever x is equal to 2, right? That's what that function is. But again, the idea is what's happening at 2, right? So if the function, if the x values approach 2, right, from the left, if I'm approaching 2 from the left, well, what are the y values doing? They're approaching this height. Similarly, if I look at the x values coming from the right, we can consider what the y values are doing from the other side. And what you'll notice there is that the function from both sides is approaching this height of 1. All right, that's the basic idea of a limit. In other words, the limit of a function at a specific value depends on what the function is doing near that x value. All right, so let's look at another example. Um, if I have g of x being equal to x cubed minus 1 over x minus 1, well, on top I have the difference of cubes, which factors out to be x minus 1 times x squared plus x plus 1, all of this over x minus 1. And what you'll note there is that the x minus 1's cancel out, giving us the equation of, the function of x squared plus x plus 1, as long as x does not equal 1. Because again, from the beginning, the domain was x cannot be equal to 1, right? Now, what this is a parabola, right? It's a parabola. And by completing the square, I can rewrite this as x plus 1/2 squared, and then that plus 3/4. All right, the process to go from this step to there would be completing the square. So what we can say now is that g of x can be rewritten as the piecewise function of x plus 1/2 squared plus 3/4 for values of x not equal to 1, and then we can say it's undefined where x is equal to 1. All right, now what would that look like on the graph? Well, let's look at it. So since I already rewrote the function using the completing the square, I rewrote it as in the vertex form, right? I can say here that the function looks something like this. It has a vertex at negative 1/2 and at the height of 3/4, right? That's where the vertex is. But notice that when x equals 1, it is undefined. So that means that if I have the value of 1 over here, then over here, there will be a hole, right? And again, the idea is the same in the sense of as we're approaching 1 from the left, what is the function doing? The function is working its way upwards this way. If I approach 1 from the right, what is the function doing? It is coming downwards towards this height. Now this height would be at the height of, well, if I were to plug in 1 into the function, I would get a height of 3, right? 1 squared plus 1 plus 1. So it would be at the height of 3. But again, it is not an actual value. It's just what the function is approaching. That's what the idea of a limit is. What is the function approaching? Not necessarily what is the value of the function at that point. So let's give a formal definition of a limit here. So definition. If f of x becomes arbitrarily close to a single number L as x approaches C from either side, then the limit of f of x as x approaches C is L. All right. Now, in symbols, we wouldn't write it like that. We would say the limit as x approaches C of f of x is L. All right. So that's just the general definition of a limit. All right. Now, what is this really showing? Well, again, that's just saying the function is approaching a specific value, whether or not That is the actual value of the function at that point. So let's talk about how to estimate a limit numerically. All right. So estimating a limit numerically. All right. So given f of x is equal to x over the square root of x plus 1 minus 1. All right. Well, we're going to answer some questions here. We're going to say find the domain. We're also going to say, so that's going to be question 1. Question 2, we're going to say find the limit as x approaches 0 of f of x. And third, we're going to say find f of 0. All right, so let's go ahead and begin answering these questions. So we said first to find the domain. So the domain is going to be, well, what do I have here? I have a fraction. And I know that whenever I have fractions, I have to make sure that my denominator is not equal to 0. So solving this, add 1 to both sides, square both sides, move the 1 over, and this should all be not equal. So x cannot be equal to 0. That's the domain. Done. Right away, we can actually answer the third question. So let's go ahead and answer the third question. Find f of 0. Well, f of 0 is undefined. How do I know that? Because, well, the domain is x cannot be 0. So what would f of 0 be? Well, you can't plug in 0 in the first place, all right? You actually end up with 0 over 0, right? If you plug it in, and that is undefined, all right? So now let's talk about question number 2. Finding the limit as x approaches 0 of f of x. So this is going to be the limit as x approaches 0 of f of x. All right, and again, f of x was, so we can write this as the limit as x approaches 0 of x over the square root of x plus 1 minus 1. All right, so in here, let's think about what it means to approach 0. All right, so let's make this table here. We're going to be approaching 0 from both ends. But because we're approaching 0, what we really want to do is we want to get values that are pretty close to 0, right? And for example, 0.01, that's pretty close to 0. 0.001, that's even closer. And I think I wrote that a little too far. So let me just write it over here. Even closer than that would be 0.0001, right? 3 zeros. And I'll just rewrite this. So that it is closer. 0.01. All right. And we actually don't even need to consider that last piece there. But that's coming from the right, right? That's to the right of 0. To the left of 0, we can apply similar things, right? We can talk about negative 0.001, negative 0.0, I missed the 0 over here. 3 zeros, 2 zeros, 1 0. And again, these are all values of x, right? Now over here, let's figure out the values of f of x, all right? And we're gonna do this one at a time. Now, normally I would have you guys plug this into your calculator so you can tell me what the values are. But because we don't have that option, I'll just tell you what happens when you plug them in. When you plug negative 0.01 in, you end up with 1.99499. When I plug the next value in, I end up with 1.99950. The next value, 1.99995. if I approach it, so from the left, we're getting slightly bigger numbers, but it's pretty clear what it could be approaching. Let's look at the right. If I start by plugging in 0.01, I end up with 2.00499. But if I approach the x values even closer, so I'm getting closer to 0, I end up with 2.00050. If I get even closer than that, I end up with 2.12340 zeros. There we go. So what you see here is we're getting closer as we're going from the left, as we're approaching 0 from the left, as well as 0 from the right. Well, what do these values seem to be going to? Well, it seems to be going to 2, right? Between 1.9995 and 2.00005 is 2. All right, so that would be the limit here. So what I can say now is that the limit as x approaches 0 of x over the square root of x plus 1 minus 1, that equals 2. All right, so that would be doing that numerically. All right, but I am not going to actually force you to do too many of these. In fact, I probably would not even put it on the test. However, I highly recommend that you do some examples like these from the homework where it it pushes you to actually plug in values like this, and it gives you a better sense of how the limits work. Because again, it's not about what the actual value of the function is at that point, it's about what it is approaching. All right, because again, notice over here, f of 0 was undefined, but the limit was 2 because the function was approaching 2. All right, so there we go. So that's one example for finding limits numerically. Now let's talk about limits that fail to exist. So it's possible for a function to not have a limit at a very specific spot. All right, and these are some possible ways that a limit can fail to exist. For example, it can have different right and left hand behaviors, or right and left behaviors. An example of a function that does that is f of x is equal to absolute value of x over x. All right. So in here, if I look at the graph, let's look at the graph. The graph of this is as follows. If I have values to the right of 0, I end up with just 1. If I have values to the left of 0, I end up with just the height of -1. But at 0, well, at 0, nothing's really happening, right? We cannot say that the limit exists because from the left, the function, what's it doing? It's staying at the height of -1. From the right, what's the function doing? It's staying at the height of +1. So in there, they are not equal to each other. So what we can say here is that the limit as x approaches 0 of the absolute value of x over x, our function, is undefined. Or we could also say does not exist. We normally abbreviate that as D and E, does not exist. All right. I'll make a note here, or I'll just briefly mention this, that this function of absolute value of x over x can be rewritten as a piecewise function as 1 for x being greater than 1, -1 for x being less than 1, for x being greater than 0 and less than 0, and then undefined for x being equal to 0. All right. So in there, we don't actually have a limit as x approaches 0. It does not exist. It could also happen with unbounded behavior. So unbounded behavior. And for that, let's look at this next function of f of x being equal to 1 over x squared. And let's look at that graph. And we're going to say, well, let's see what happens as it approaches 0. So the limit as x approaches 0 of 1 over x squared. This turns out to be undefined. And why would that be? So let me show you the graph. The graph of this looks like this. So this is 1 over x squared. All right. And if you'll notice, as we're approaching 0 from either side, right, it gets bigger and bigger. It actually goes to positive infinity from either side. So what we're actually going to say here is, well, technically, it is infinity, but positive infinity. But we're going to say that that is undefined, so it does not exist. And why would we say it does not exist when it's positive infinity? Well, if you recall, let me scroll up. If you recall, I said in the definition of a limit that it needed to approach a specific number, L, right? The thing about infinity is that infinity is not a specific number. It's not a single number. Infinity is just the idea of numbers getting bigger and bigger, but it is not a specific value. It is not a fixed value. So because of that, we would say it does not exist here. All right. Even though from both sides it's going to positive infinity, we would still say it does not exist. Another possible way to have a limit fail would be having oscillating behavior. Right? And the most common example for that one is something like f of x being equal to sine of 1 over x. Just like in the previous examples, notice that this is not defined at x equals 0, so we're going to take the limit as x goes to 0 of sine of 1 over x. All right. Now let's think about let me show you what that looks like. All right. So this function looks something like this. All right. It's bounded between 1 and -1, right? And it looks something like this. It oscillates a lot as it gets closer and closer, but then it it oscillates slower as it gets further and further from 0, from the x value of 0. All right. Now the problem with that is that, well, at 0 it is technically undefined, right? Because you can't plug it in. So in here at the actual y-axis, there's a hole somewhere. But the thing is, you can't really figure out what that hole is because it's just oscillating faster and faster. All right. So it's not at any specific height. So in here, we would also say that the limit as x approaches 0 of this function is undefined, or again, does not exist. All right. So those are some possible ways for the limit to fail to exist. So essentially, where we have jump discontinuities, where we have vertical asymptotes, where we have behavior that we can't really tell what it's actually doing um, at those specific values. All right. So overall, that's how a limit can fail to exist. So now let's give the formal definition of a limit. The formal definition of a limit, of limits. So let f be a function defined on an open interval containing c, except possibly at c. So it's defined throughout the entire interval that C is a part of, but it might not necessarily be defined at C. So except possibly at C itself, and let L be a real number. The statement limit as x approaches C of f of x equals L means that for each epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus c is between 0 and delta, so it's bigger than 0 but less than some delta, then the absolute value of f of x minus L is less than epsilon. All right, so that is the formal definition of a limit. All right, if the absolute value of x minus c is between 0 and delta, then the absolute value of f of x minus L is less than e. So let me give you a visual as to what this is talking about. All right, so let's say that we had our function on the xy plane, right? So let's say that we have some sort of function. All right, and let's make it smaller, something like that. All right, so in there, if you know what, I changed my mind. Let's do that one. So let's look at some value c. So perhaps I'll do that in yellow. Let's look at the value c. All right, and we're talking about being very, very close to C, right? Because delta just represents some tiny number, right? And here, the distance between X and C is very small. So we can talk about is, let's say, for example, that this is delta. That's the distance of delta. So over here is delta. So over here, this value over here, this one is C minus X. And this one over here is not C minus X, C minus delta, and this one over here is C plus delta, all right, where any given value here is just X overall. So I'm just going to call this some generic X, all right. Now in here, well, this value up here, that is going to be our limit L, all right, and what we're saying is that L is some epsilon away from our function. All right, so in here we're saying this is epsilon and this is epsilon. And what we're essentially saying is that we can get arbitrarily small here, all right, depending on what values of delta and epsilon we choose. So again, all it's really saying is as we're getting arbitrarily close to the x values along the x-axis, then the limit of the function is whatever value we're getting arbitrarily close to, all right, whatever y value. So let's see an example. So in here, we're going to say use the epsilon delta definition of a limit to prove, so this is example C, to prove that the limit as x approaches 2 of 3x minus 2 is 4. All right, so we're gonna do this, and we're gonna do this using the epsilon delta definition. All right, so let's see what happens here. What I'm going to start with, so let's start with what we want to show. We want to show WTS. I use that to stand for want to show. We want to show that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. All right, what does that mean in terms of this? All right, in terms of this actual limit, what we're saying is we want to show that if we're taking that if we're in the absolute value of x minus 2, because that's what we're approaching, if that's less than some delta, then the absolute value of f of x, which is 3x minus 2, and then that minus our limit, which is 4, that is somehow less than epsilon, all right? So let's see what happens here. Well, we've got this statement over here. That's what we want to show is true. We want to force that to be true. The question is, how do we force that to be true? Well, let's do some arithmetic. If I take the absolute value of 3x minus 2 and then that minus 4, well, what does that give me? That gives me the absolute value of 3x minus 6. I can rewrite this now as 3 times the absolute value of x minus 2, right? In there, all I did was factor out the 3, right? Now, in here, we want this, so we want that 3 times the absolute value of x minus 2, we want that to be less than epsilon. That's what we want. What do we know for sure, though? We know that the absolute value of x minus 2 is less than delta. So what we can say here is we can combine these two statements and say, well, 3 times the absolute value of x minus 2. Well, so let me rephrase that. We can combine those, we can use the bottom line to show that the top statement is true. So maybe I'll do that on the next line. So 3 times the absolute value of x minus 2, that would be less than 3 times delta, right? Because x minus 2, the absolute value of x minus 2 is less than delta. So 3 times that value would be less than 3 times delta. And we want that to be less than epsilon. So what we can say is, well, let delta be less than or be equal to epsilon over 3, right? At that point, well, this statement ends up being completely true, right? Because if I have 3, I should say less than. If I have delta being epsilon over 3, then as long as I choose something smaller than that, then we're going to be fine here. So what we can say now is that, well, let me put this all together. So thus, if I take the absolute value of x minus 2 being less than delta, which we know to be epsilon over 3, then this implies now that the absolute value of 3x minus 2 minus 4, which is equal to the absolute value of 3x minus 6, which is equal to 3 times the absolute value of x minus 2, which that would be less than 3 delta, which again is equal to 3 times epsilon over 3, which is epsilon, which is what we wanted to show. We wanted to show that that somehow ended up with being less than epsilon. Let me just fix something here. I definitely meant equals, even though I said less than, but I definitely meant equals there. Anyway, so that's what we end up with there. Now, as far as using the epsilon delta definition of a limit, that's essentially what you do. All right, you manipulate the expression in such a way that you end up with just epsilon at the very end. Now, so that was C. So now let's do D. So what if I want to find a specific value of delta for a specific given value of epsilon? So finding a delta given epsilon. So given that the limit as x approaches 3 of 2x minus 5 is equal to 1, find delta such that the absolute value of 2x minus 5 minus 1 is less than 0.001 whenever the absolute value of x minus 3 is less than delta. All right, so here we go. Here is our solution for this. So solution. So if I start with this absolute value, so I have the absolute value of 2x minus 5 minus 1, right? If I combine things there, I end up with the absolute value of 2x minus 6, which is 2 times the absolute value of x minus 3, all right? All I did there was factor out the 2. So in here, what does that tell me? Well, I want this to be less than 0.01, right? We want to have 2 times the absolute value of x minus 3 be less than 0.01. So that means that what we really want is to have 2 times some delta be less than 0.01. So from there, dividing both sides by 2, that gives me that delta. And by the way, how did I replace that delta there? Over here, all right? So 2 times delta would be less than 0.01, so delta would be less than 0.005, because that's what 0.01 divided by 2 is. All right, so there we go. So we just have to choose a delta that's less than 0.05. Now, graphically, what did we just find? All right, so let me show you what this means graphically in this specific example. So if I look at the graph of this function, all right, the function looks something like this. So we have 2x minus 5, that is something like this. And now I'm just going to do a generic idea here. All right, that would be f of x is equal to 2x minus 5. All right, that was our function. So what are we really saying here? We were approaching the value of 3. All right, so let's say here's 3. And what happens here is, well, we were given that the limit is 1. So that means that it should be approaching the value of 1. Now, what we're actually saying here with all this delta epsilon stuff, what we're saying is that as long as we're staying within delta distance from 3, we should be staying within epsilon distance of 1. All right, that distance is epsilon. Um, so in here, that is the actual value. And we're saying again, well, what did we find here? What we found here is that as long as, since delta was 0.005, as long as we're staying within 0.05 units, so this right here is 0.005, as long as we're staying within that distance of 3, we're guaranteed to stay epsilon units away. And the epsilon was, well, what was epsilon? I guess 0.01. There we go. This appears epsilon. So we're guaranteeing that we're going to stay within 0.01 units of 1. So that's what this showed, right? Now, again, with the epsilon delta definition stuff, I highly recommend that you go through a couple of examples. It does take some time to get used to working with this kind of problem. But anyway, let's do a different kind of example, something a lot more visual. So example E. Let's say that you had this graph, all right? Uh, Something like this. And well, I'm gonna try to make this kind of accurate. So each tab here is value of 1. And let's say that it does something like this. Let's say that it has a vertical asymptote here. Well, maybe I'll do that in a different color. We're going to have a vertical asymptote. All right. We're going to have our function do something like this. And we're going to have another vertical asymptote over here. And let's fill this up here. All right. So that's what our function looks like. All right. And this is a function. All right. It passes the vertical line test. So it is definitely a function. Now, and again, each little tick mark is a value of 1, so on and so forth. So what we can do here is ask a bunch of questions about this graph. So the first question I can ask here is, well, what is f of -2? And if you go to -2 here, you see that we have a vertical asymptote. So clearly f of -2 is undefined. And I will call this A. I'll call this question 1. Question 2. We can ask, well, what is the limit as x approaches -2 of our function? And recall that the limit was, well, what is the function doing? Well, let's look at what's happening from the left and from the right. So from the left, we're approaching the left, we're approaching -2 from the left, and the function is going to -infinity. When we're approaching to -2 from the right, it is approaching positive infinity. So, and here we could also say again, it is undefined or does not exist. All right. Same with this one. So now, so that's question 2. Well, to keep this everything on the same page, I'll do question 3 over here. Question 3, what we can say is, well, what is f of 0? And well, if we go to 0, right? If we go to 0, the x value is 0. What happens when you plug? Well, what is the actual value? Well, this is an open circle, so there's nothing there. But this is a closed circle, so there's definitely something there, and that is at the height of 4. All right? That would be f of 0. If we look at the limit as x approaches 0 of our function, well, let's look at that. We're approaching 0 from the left. What's the function doing? It's getting closer and closer to the height of 1. If we approach 0 from the right, what's the function doing? It's getting closer and closer to the height of 4. So this is a jump discontinuity. It does not, so when that happens, where you know that the limit does not exist, so we can just go ahead and write does not exist. 5. We could ask for, well, what is f of 2? Well, f of 2, well, we go to the value of 2 and look at the function. There's an open hole there, so it is undefined. The function is not defined there. But we could ask, well, what's happening as we get closer and closer to it? In other words, what is the limit as x approaches 2 of the function? And if we're approaching 2 from the left and from the right, Well, the function either way is getting to this height, right? This height of 1. So that would be 1. Maybe I'll fit 2 more questions here. If I could also ask, well, what is f of 4? F of 4, well, at 4 we have a actual value there. There's a vertical asymptote, but we actually have a value there. So the actual value of f of 4 would be at this height of 3. All right? And I should have done that in yellow. So f of 4 is 3. The next thing we can ask here is, what's the limit as x approaches 4 of our function? All right, and that's a 4. Well, what's happening here? From both sides, it's going to positive infinity, right? Here's the value of 4 as an x value. When we're approaching it from the left, it's going to positive infinity. Approaching it from the right, it's going to positive infinity. So technically here we would say this is positive infinity, but we would say the limit does not exist, all right, because it's an infinity. And that is the end of 2.2, all right? And essentially, again, what we did there was, in this last example, was graphically show why the limits are what they are, all right? So just from reading the graph, we're able to figure out a bunch of different questions there.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.